This video describes how to conduct 3 of the most popular submaximal tests for endurance or aerobic fitness. This is often measured using either maximal laboratory or field tests, which may be quite unsuitable for some populations. Advantages of submaximal tests. While there is a great variety of test protocols that could be used to assess maximal aerobic power, submaximal testing is often preferred because it involves less risk, is less intimidating, particularly for members of the general population, is less disruptive to training, is reliable and valid if subject controls and technical considerations are strictly adhered to. Some of these issues are discussed in more detail later in the presentation. Advantages of the cycle ergometer. Ideally, the ergometer chosen for testing purposes needs to be specific to the requirements of the athlete or sports person. However, the cycle ergometer is often used with the general population for the following reasons. The body weight is supported, a particularly important point for the very overweight. Little skill or learning is required of the subject. Cycling efficiency is relatively constant and predictable. Workloads can be easily measured and manipulated, and the subject's upper body remains reasonably stationary, enabling measurement of physiological variables such as heart rate and blood pressure to be made quite easily. Subject preparation. The tests described in this program rely on accurate measurement of heart rate to assess aerobic fitness. It is therefore important to control for all factors which would affect heart rate other than the exercise task itself. With this in mind, the subject should not have exercised vigorously for at least 2 hours prior to testing, and ideally not at all on that day. Not have eaten for at least 2 hours before testing. However, it is important to drink to satisfy thirst, and not to have consumed stimulants such as tea, coffee, nicotine or alcohol for at least 2 hours before testing. In addition, the subject should be dressed in comfortable light clothing which will not impede cycling. Environmental test conditions should be maintained at between 18 to 22 degrees centigrade with a relative humidity less than 60%. For instance, research has indicated that at a constant workload, heart rates rise by 1 to 2% for every 1 degree centigrade rise in ambient temperature above 21 degrees centigrade. Thorough calibration procedures must be conducted on a regular basis. The subject should be habituated to the test to minimize the effects of anxiety on heart rate. At least one familiarization session should be held before the actual testing. As heart rate undergoes minor variation during a typical day, any retests of a subject should ideally occur at the same time of the day. Finally, the subject's nude mass must be measured before the test begins. First, weigh the clothing and footwear to be worn on a small set of scales. Then, weigh the clothed subject on the electronic laboratory scales. Record the mass to the nearest 0.05 kilograms. Nude mass is obtained by subtracting the mass of the clothing from the mass of the clothed subject. Assumptions of submaximal tests. When predicting maximal aerobic power, or VO2 max, from a submaximal cycle ergometer test, at least 3 important assumptions are made. For this prediction to be valid, these assumptions must be satisfied. First, that there is a linear relationship between heart rate, power output and oxygen uptake in the submaximal work state. Second, that maximal heart rate for any particular population of subjects are extremely similar. And third, that the oxygen uptake at submaximal standard work rates are also very similar for that same population. If we intend to predict maximal aerobic power from submaximal tests, satisfaction of these assumptions is essential. Introduction to submaximal cycle ergometer tests. The PWC 170 test was developed in the late 1940s and, as its name suggests, it identifies the subject's physical work capacity corresponding to a heart rate of 170 beats per minute. By 1954, the Ostrand test had been developed and it remains one of the best estimations of aerobic fitness. More recently, researchers at the Australian Institute of Sport in Canberra have developed the tri-level profile of general fitness. And the aerobic power index of this three-part test battery has proved to be an excellent submaximal test for assessing aerobic status. The test is conducted on an air-braked cycle ergometer and will be the first test presented in this video. Aerobic power index of the tri-level fitness profile. Briefly, the test requires the subject to pedal the ergometer at a power output of 25 watts for the first minute, with this workload increasing by 25 watts every minute until a target heart rate is achieved. It is the power output associated with this target heart rate that is the aerobic power index. To calculate the target heart rate, apply the following formula. Target heart rate equals 220 minus age multiplied by 0.75. By attaching a work monitor unit, power output can be accurately calculated by measuring the work done each minute in kilojoules and converting this data to watts. Before starting the test, adjust the seat so that the subject is in a comfortable pedaling position. The leg should be slightly flexed when the pedal is at its lowest position. Record this seat height for future reference. Fit a heart rate monitor if you have one, or check that the pulse can be found using palpation or a stethoscope. Start pedaling at 25 watts and activate the stopwatch. At the end of the first minute, observe and record the heart rate, then increase the power output to 50 watts. This increase in power output of 25 watts every minute continues until the target heart rate has been achieved or passed. The test is concluded at the end of the minute during which the THR is achieved. To establish the aerobic power index, determine the actual power output at which the THR is achieved by interpolation. Here is an example. If the subject's age is 20 years, then the target heart rate is 220 minus 20 multiplied by 0.75 or 150 beats per minute. Let's say that in the 6th minute the power output was 150 watts and the heart rate plateaued at 146 beats per minute, while during the 7th minute the heart rate plateaued at 154 beats per minute at the power output of 175 watts. By interpolation, the target heart rate of 150 lies 4/8 or halfway between 146 and 154. Therefore, the associated power output is halfway between 150 and 175 watts, that is 162.5. Hence, the aerobic power index for this subject can be rounded off to 163 watts. This absolute result can be made relative by dividing by the body weight to produce a result in watts per kilogram. The following table provides typical aerobic index scores in watts per kilogram for teenagers and young adults. Ostrand cycle ergometer test. The next test to be presented is the Ostrand cycle ergometer test, which enables maximal aerobic power in litres per minute to be predicted from the steady-state heart rate response to a 6-minute single power output on a Monarch cycle ergometer. The subject cycles at 50 revolutions per minute against a resistance sufficient to elevate the heart rate to between 130 and 170 beats per minute. As a guideline, these resistances are likely to be 1 kilopond for females under 60 kilograms and 1.5 kiloponds if over 60 kilograms, whereas males should apply 2 kiloponds if under 70 kilograms and 3 kiloponds if over 70 kilograms. These are only guidelines, and the optimal resistance will vary with body mass and fitness level. Subjects who are regular cyclists will display low heart rate responses to submaximal power outputs and will therefore require increased resistance. They may also display unrealistically high VO2 max data. To conduct the test, first adjust the seat height as previously described. Record this seat height for future reference. Once a heart rate monitor has been fitted to the subject and checked for accuracy, you are almost ready to start the test. Note and record the pre-test heart rate. Since the pedalling speed is to be 50 revolutions per minute, a metronome or a cat-eye will be required to establish this cadence. If using the electronic metronome, set the device at 50 RPM and adjust the volume so it can be clearly heard during the test. Reset the revolution counter on the ergometer. You will need to measure the actual number of pedal revolutions completed during the test. This is required for accurate power output calculations. You are ready to start the test. The subject begins cycling at the designated cadence while the resistance is set. At this stage, assure the subject that they can take time to adjust to the workload without affecting the end result. When the subject is stable, check that the heart rate is being displayed and then simultaneously start the stopwatch or clock while reading the revolution counter. The test now proceeds at this same power output for 6 continuous minutes. Monitor the subject throughout the test, but avoid engaging them in long conversations. Also ensure that the resistance set on the Monarch remains at the prescribed level. If the applied resistance is not stable, then the belt around the flywheel will most likely require replacement. During the test, you will need to record the following data: heart rate each minute, if not from the sport tester, from palpation or a stethoscope. With both these latter techniques, take a 15-second measurement and multiply by 4. Total pedal revolutions, these must be recorded at the end of the test. Since the plateau or steady-state heart rate is required at the submaximal power output, the test is ended if the difference in heart rate between the 5th and 6th minute is 2 beats per minute or less. If the heart rate rise is greater than this, you will need to continue the test for another minute. At the end of the test, encourage the subject to cycle down gradually rather than stop suddenly. It is important to continue to pay attention to the subject until he or she has finally dismounted from the cycle ergometer. You now have sufficient data to predict the subject's maximal aerobic power using the Ostrand nomogram, that is, power output in watts, steady-state heart rate, age, body mass in kilograms, and gender. Using the Ostrand nomogram. The Ostrand nomogram is gender-specific and was constructed around a population of 25-year-olds, which means the result from the nomogram will require an age correction factor unless the subject is 25 years of age. On the left side of the nomogram is the pulse rate. Identify the correct column for the subject's gender and mark the steady-state heart rate achieved. Over on the right is the work rate in watts. Again, identify the correct column for the subject's gender and mark the power output achieved. Note that the watts increase in increments of 5. A horizontal line should be drawn to the far left side of this column. It is this point we shall use to connect the power output achieved to the steady-state heart rate. Now, join the marked heart rate to the appropriate power output. This line will pass through the predicted VO2 in litres per minute. You now have your absolute maximal aerobic power score. But unless the subject is 25 years old, this data will have to be corrected for age. Refer to the age correction factor table. For example, if the subject was 20 years of age, this factor would be 1.05. If they were 35 years of age, it would be 0.87. Multiply the absolute maximal aerobic power in litres per minute by this factor. This is the final result. If you wish to convert this data to a relative measure, then the result should be multiplied by 1,000 to change to mils, and then divided by the body mass to achieve a relative score in mils per kilogram per minute. The relative measure of maximal aerobic power is ideal for comparison purposes. The following table provides typical values of maximal aerobic power in mils per kilogram per minute for teenagers and young adults. Remember that the tests we are describing are cycle tests and may therefore favour those accustomed to cycling. The modified Sjöstrand PWC 170 test. The major difference between this test and the Ostrand is that the subjects complete 3 submaximal workloads, each of 4 minutes duration. For each of these workloads, a steady-state heart rate is recorded, and the PWC 170 is determined by constructing a graph from this power output and heart rate data. The subjects pedal continuously for the 12 minutes of the test at a pedaling rate of 60 revolutions per minute. Subject preparation is exactly the same as for the previous tests. With the subject seated on the Monarch ergometer in a comfortable riding position, instruct him or her to start pedaling at 60 RPM. This rate can be set by a metronome, cat-eye or the Speedo, which should read 22 kilometers per hour. Ensure the revolution counter is operating and then apply the first resistance, usually 0.5 kilopond for females and 1 kilopond for males. When stable at this power output, start the time and reset the revolution counter simultaneously. The revolutions must be read exactly at the end of the 4th, 8th and 12th minute, and the resistance increased at the same time to generate heart rates of 110 to 130 by the end of the 4th minute, 130 to 150 by the end of the 8th minute, and 150 to 170 by the end of the 12th minute. The resistance setting must be set accurately and monitored during the test. Record the heart rate at the end of each minute to establish that it is in the required range and that steady state has been achieved. Very occasionally, an extra minute of cycling is required to meet these conditions. Remember, in this case, the pedal revolutions will be for 5 minutes and not 4. It is important that this test is kept submaximal, and the final workload can sometimes cause problems by exceeding 170 beats per minute. This situation can be easily avoided by actually calculating the resistance in kiloponds for the last workload using the data from the 2 previous workloads. This can be done because of the linear relationship. For example, if 1 kilopond produced a heart rate of 120 beats per minute, 2 kiloponds 150 beats per minute, clearly 3 kiloponds would put the heart rate to an excessive 180 beats per minute, whereas 2.5 kiloponds would produce an ideal 165 beats per minute. At the completion of the 3rd 4-minute workload, the test is concluded. Release the resistance on the bicycle ergometer and encourage the subject to cycle down for a few minutes. To determine the PWC 170, calculate the power outputs for the 3 workloads using the resistance and RPM data, and plot these against the steady-state heart rate data. This relationship should be linear, And if this is the case, draw a line of best fit through all 3 points. To determine the PWC 170, simply identify the power output associated with a heart rate of 170 beats per minute. In most cases, the 3 points will not sit exactly on a straight line. You can make a reasonable estimation of the relationship by using a line of least squares. To do this, connect the first and third data points with a straight line. Let's call this line A. Now, draw a line from the middle data point perpendicular to line A. We'll call this line B. Carefully measure 1/3 of the distance along this line B towards the middle data point. The line of least squares is now drawn through this point parallel to line A. It should be pointed out that one of the assumptions outlined earlier was the linear relationship between heart rate and power output, so these plotted points should not be far from linearity or the test would be invalid. The following table provides typical PWC 170 scores in watts per kilogram for teenagers and young adults. However, you can convert the data to a predicted maximal aerobic power from the Ostrand nomogram. Using the heart rate of 170 and the associated power output, you can estimate the VO2 max in litres per minute. Don't forget that the raw data is gender-specific, and of course the answer will need to be corrected for age. You may have subjects who have PWC 170 scores in excess of 250 watts. The Ostrand nomogram only caters for power outputs to 250 watts. This should not create a problem since the relationship between heart rate and power output is linear. You can simply determine the heart rate response to, say, 200 watts and use this data on the nomogram. So, how did your subject rate? The level of aerobic fitness required will be specific to the needs of the individual. Some examples of maximal aerobic power for high-level performers in different sports are shown. These examples will provide some insight into the fitness status of the subject you have tested.